Now that we have established the hyperbolic functions in the previous lesson, we are now ready to talk about them in terms of calculus, namely the derivatives and integrals and how they apply to the hyperbolic functions. Perhaps not surprisingly, the derivatives of the hyperbolic functions actually behave in similar ways to the derivatives for trigonometric functions. That would seem to follow, given that the hyperbolic functions have identities that follow directly from what we saw in trigonometric functions. So it's perhaps not surprising that these would work in a similar fashion. To start with, I will make the claim that the derivative of hyperbolic sine of x is equal to hyperbolic cosine of x, which is exactly how it would work with trigonometric functions. So it might not be surprising that it would work in a similar way here. That being said, how can we be sure? It behooves us to actually prove this, which is easy enough to do using the algebraic form of hyperbolic sine of x. So that will be the first step, is to rewrite hyperbolic sine of x in its algebraic form, e to the x minus e to the negative x over 2. The denominator represents a multiplication by 1/2, which thus carries through to the derivative. The numerator then can be differentiated term by term, where the derivative of e to the x is e to the x, minus the derivative of e to the negative x, which would be e to the negative x times the derivative of the exponent, which is -1. Thus we have minus negative e to the x in the top becomes plus e to the negative x. And this is the algebraic form of hyperbolic cosine. Now, lest you go thinking this is all 100% like the trigonometric functions, we should now look at the derivative of hyperbolic cosine of x, which, as we're going to see, is not negative hyperbolic sine of x. It is simply hyperbolic sine of x. We do not pick up a negative sign as we would have with trigonometric functions. And again, the proof is easy enough. Actually, it's going to be incredibly similar to the proof of the derivative of hyperbolic sine of x, because the two algebraic formulas are virtually identical. In fact, the only place where they differ is in addition versus subtraction in the numerator. Like before, the 2 in the denominator represents a multiplication by 1/2 and therefore carries straight through to the derivative. In the numerator, the derivative of e to the x is e to the x, plus the derivative of e to the negative x, which we saw before is negative e to the negative x. The only way this could possibly have resulted in negative hyperbolic sine of x is if the entire numerator changed sign, but it doesn't. It's only that second term that is changing sign between positive and negative. And when it does so, all that does is cause this to swap back and forth between hyperbolic sine and hyperbolic cosine. So in terms of derivatives, the derivative of hyperbolic sine and the derivative of hyperbolic cosine simply are each other. No negatives picked up along the way, which certainly makes our lives a bit easier. On the other hand, it does make this easy to confuse with the derivatives of the trigonometric functions, so be very careful. As for the other four, they can all be done using the quotient rule in conjunction with the two derivatives we just showed. The derivative of hyperbolic tangent can be done using the quotient rule with hyperbolic sine of x over hyperbolic cosine of x. So we have the denominator, hyperbolic cosine of x, times the derivative of the numerator, which, as we just showed, is, again, hyperbolic cosine of x, minus the numerator, hyperbolic sine of x, times the derivative of the denominator, which, as we just showed, is hyperbolic sine of x, all over the denominator squared. To simplify the top a bit, we have hyperbolic cosine of x squared minus hyperbolic sine of x squared. Now, again, be careful. The hyperbolic identities are not exactly the same as the trigonometric identities in all cases. For trigonometric identities, if we had cosine squared plus sine squared, we'd be able to use Pythagorean identity. But for hyperbolic functions, remember, we're looking for minus. Hyperbolic cosine squared minus hyperbolic sine squared is the equivalent of the Pythagorean identity and is actually just equal to 1. And 1 over hyperbolic cosine squared is hyperbolic secant squared, which again should look familiar then. The derivative of hyperbolic tangent is hyperbolic secant squared. Without going through all of the others, in terms of proving them, the derivative of hyperbolic cotangent of x is going to again result in hyperbolic cosecant squared. This time we do pick up the negative. The reason actually isn't in the derivatives of the hyperbolic sine and the hyperbolic cosine. The reason we pick up the negative here actually has to do with what's going on in the numerator of the quotient rule. I leave that to you to show why it would come out with a negative, but it has to do with the numerator of the quotient rule. So if you want to try it, it's not a terrible idea to give that a shot. Next, we have hyperbolic secant, which, perhaps not surprisingly, is going to result in hyperbolic secant times hyperbolic tangent, except this time, unlike the trigonometric functions, this does pick up a negative. Again, the reason for that can be found in the numerator of the quotient rule, in conjunction with the fact that instead of cosine squared plus sine squared, we're now looking for hyperbolic cosine squared minus hyperbolic sine squared. Lastly, we have the derivative of hyperbolic cosecant, which is negative hyperbolic cosecant x times hyperbolic cotangent x. So there are definitely some differences. The base derivatives are the same, but we have some differences in the positives and negatives. Each of the reciprocal functions here results in a negative derivative, whereas each of the original three results in a positive. So not exactly the same, many similarities, but enough differences that we need to be careful in what we do. Of course, each of these differentiation statements can be turned around to become a integration statement. For example, if we have the derivative of hyperbolic sine of x is equal to hyperbolic cosine of x, then an equivalent integration statement to that would be that the antiderivative of hyperbolic cosine of x dx would be equal to hyperbolic sine of x plus c, of course. Likewise, the statement that the derivative of hyperbolic cosine of x is equal to hyperbolic sine of x has the equivalent integration statement that the antiderivative of the hyperbolic sine of x dx is equal to hyperbolic cosine of x plus c. If the derivative of hyperbolic tangent of x is equal to hyperbolic secant squared of x, then the equivalent integration statement would be that the antiderivative of hyperbolic secant squared of x dx is equal to hyperbolic tangent plus c. The derivative of hyperbolic cotangent of x is equal to negative hyperbolic cosecant squared which means that the antiderivative of hyperbolic cosecant squared of x dx would be equal to negative hyperbolic cotangent of x plus c. The derivative of hyperbolic secant is negative hyperbolic secant times hyperbolic tangent, which means that the equivalent integration statement is that the antiderivative of hyperbolic secant of x times hyperbolic tangent of x dx is equal to negative hyperbolic secant of x plus c. And lastly, the derivative of hyperbolic cosecant of x is negative hyperbolic cosecant of x times hyperbolic cotangent of x, has the equivalent integration statement that the antiderivative of hyperbolic cosecant of x times hyperbolic cotangent of x dx is equal to negative hyperbolic cosecant of x plus c. Beyond this, all of the regular differentiation rules apply, and the integration rules. Specifically that we can use the chain rule if we have a composition, the product rule if we have a product, the quotient rule if we have a quotient. A couple of examples. The derivative with respect to x of hyperbolic sine of x squared minus 3 by the chain rule, we would have the derivative of the outer function, which is hyperbolic sine. The derivative of hyperbolic sine would be hyperbolic cosine, and that would be composed with the original inside function x squared minus 3. And then that would be multiplied by the derivative of x squared minus 3, thus giving us, by the chain rule, simply 2x times hyperbolic cosine of x squared minus 3. Nothing special, nothing fancy. Another example. Suppose we are looking for the derivative of x minus 1 times hyperbolic cosine of x minus hyperbolic sine of x. The first term of this is a product, which will therefore require the product rule. The first function is x minus 1, and that is multiplied by the derivative of the second function. The second function being hyperbolic cosine of x, its derivative is hyperbolic sine of x. Plus the second function, hyperbolic cosine of x, times the derivative of the x minus 1, minus the derivative of hyperbolic sine of x, which is simply hyperbolic cosine of x. We get a clean cancellation of these two terms, which means the derivative of this function is simply x minus 1 times hyperbolic sine of x. In terms of integration, suppose we have the antiderivative of hyperbolic cosine of x times hyperbolic sine squared of x dx. A quick substitution here of u is equal to hyperbolic sine of x, so that du is equal to hyperbolic cosine of x dx will allow us to rewrite this integrand as u squared times du. So again, same basic integration technique of integration by substitution. A power rule to find the antiderivative, and then a resubstitution at the end to return to the original variable. So again, nothing new in terms of differentiation or integration techniques, just new functions to work with. Now, unfortunately, it doesn't stop there. Because not only do we have the hyperbolic functions, we also have their inverses. Now, a lot of these are actually going to look similar to the derivatives and antiderivatives of the inverse trigonometric functions, interestingly enough. However, there are some important differences. So we're going to start with the derivatives of the inverse hyperbolic functions and then come back and be able to compare them to the inverse trigonometric functions. The derivative of inverse hyperbolic sine of x is equal to 1 over the square root of x squared plus 1. The derivative of inverse hyperbolic cosine, is equal to 1 over the square root of u squared minus 1. The derivative of inverse hyperbolic tangent is equal to 1 over 1 minus x squared. Excuse me, I wrote a u up here. That should have been an x. Now, interestingly enough, the derivative of inverse hyperbolic cotangent is actually also 1 over 1 minus x squared. However, remember that inverse hyperbolic tangent and inverse hyperbolic cotangent had disjoint domains. Inverse hyperbolic tangent was only valid for values between -1 and 1, whereas inverse hyperbolic cotangent was only valid for values exceeding -1 and 1. So yes, they both have the same formula, but they are only valid for different input values. We then have the derivative of inverse hyperbolic secant, which is -1 over x times the square root of 1 minus x squared. And the derivative of inverse hyperbolic cosecant of x, which is equal to -1 over the absolute value of x times the square root of 1 plus x squared. Now, these differ from the derivatives of the inverse trigonometric functions in important ways. The derivatives of the inverse trigonometric functions include the derivative of inverse sine or arc sine, which was 1 over the square root of 1 minus x squared. Please note that as similar as this looks to some of the others, there isn't a single function in here that has 1 minus x squared in that order under the square root, except for inverse hyperbolic secant, which also has a factor of x in front of it. Thus, we are looking at two different forms. The negative notwithstanding, we are looking at two different forms. They may share the square root, but the extra factor of x outside the square root makes them very different. The derivative of arc cosine is the same as the derivative of arc sine, just with a negative. The derivatives of arc tangent and arc cotangent are again very similar. They are 1 over 1 plus x squared. Now again, the only two here that are similar to it are the inverse hyperbolic tangent and inverse hyperbolic cotangent, but note that they are not addition. They are subtraction, 1 minus x squared, as opposed to 1 plus x squared. And lastly, the arc secant and arc cosecant functions, differing only by a negative, are 1 over the absolute value of x times the square root of x squared minus 1. Where again, there is no other denominator in here that exactly matches that. The inverse hyperbolic cosine does have the same radical factor in the denominator, but it is lacking the absolute value of x. And the inverse hyperbolic secant is very similar to this, but it has the subtraction in the other order. Between these 9 formulas, or 12 if you count the positives and negatives of the inverse trig functions, they account for every combination of addition of squares, subtraction of squares in both orders, underneath a radical, or not underneath a radical, with an extra factor of x in front of the radical, or without an extra factor of x in front of the radical. So this has expanded our ability to do different integrals, and each of these can still be done with trigonometric substitution, because they all fit the form of a sum or difference of squares. Of course, the hyperbolic ones are going to produce hyperbolic functions when we integrate, whereas the others will produce inverse trigonometric functions when we integrate. The integrals of these things are not pretty then. So the difference between the derivative of hyperbolic sine, inverse hyperbolic sine, and inverse hyperbolic cosine is simply whether it is x squared plus 1 or x squared minus 1 under the radical. As it turns out, we can group them into a single definition, allowing for other terms there besides just a 1. It can be anything squared. And this can be plus or minus. This would result in either inverse hyperbolic sine or inverse hyperbolic cosine. But inverse hyperbolic sine and inverse hyperbolic cosine differ only by one small thing, namely the sign underneath the radical. And it just so happens that the positive or negative sign under the radical in the integrand directly corresponds to the positive or negative sign under the radical in the antiderivative. We can handle the other two, the other pairs of inverse hyperbolic functions in the same way. If we have a difference of squares where the constant term comes first, this would be equal to 1 over 2a times the natural logarithm of the absolute value of a plus x over a minus x plus c. If you recall, the derivatives of the inverse hyperbolic tangent and inverse hyperbolic cotangent were the same. So their integrals are going to be the same. The logarithmic form of inverse hyperbolic tangent and inverse hyperbolic cotangent differed only by the order of subtraction in the denominator. The absolute value means that the order of subtraction in the denominator is irrelevant to the integral. That's why we can have a single integrand producing essentially two different antiderivatives depending on what the value of x was, depending on the domain. Remember that inverse hyperbolic tangent was valid for values smaller than 1 in magnitude, and inverse hyperbolic cotangent was valid for values exceeding a magnitude of 1. The third pair then, 1 over x times the square root of a squared plus or minus x squared dx. We have a similar situation here to what we saw with inverse hyperbolic sine and inverse hyperbolic cosine. We see it again with the inverse hyperbolic secant and the inverse hyperbolic cosecant. They have very similar derivatives, differing only by a plus or minus under the square root. Therefore, their antiderivatives can be grouped by whether they have a plus or a minus under the square root. And they both produce negative 1 over a times the natural logarithm of a plus the square root of a squared plus or minus x squared over the absolute value of x plus c. Where again, we have the plus or minus in the integrand corresponding directly to the plus or minus under the radical in the antiderivative. And again, the same rules apply in terms of integration rules. For example, suppose we have the antiderivative of 1 over x times the square root of 4 minus 9x squared dx. We can rewrite the integrand then by writing each of the terms under the radical as something squared. The 4 can be written as 2 squared. The 9x squared can be written as 3x squared. A little bit of substitution here to help us out. U is equal to 3x, so that du is equal to 3dx. Since there is a lack of a factor of 3 to take out, we can divide both sides by 3 here and have 1/3 du is equal to dx. This can then be written as 1/3 times the integral of 1 over, well, we'll come back to the x in a moment. Here we have the square root of 2 squared minus u squared. And we do have that extra factor of x out there, which means we need to come back to our substitution and divide both sides of the u equals 3x by 3. And that gives us a way to remove the x factor in the denominator and replace it with 1/3 times u. But when that happens, we have a 1/3 in the top and bottom, canceling each other out. So we are now left with the antiderivative of 1 over u times the square root of 2 squared minus u squared du. And this fits exactly the format that gave us the antiderivative that resulted in an inverse hyperbolic secant or inverse hyperbolic cosecant, depending on the sign under the radical, in this case, a subtraction. Which means that our antiderivative, by the formula on the previous page here, would then be negative 1 over 2 times the natural logarithm of 2 plus the square root of 2 squared minus u squared over the absolute value of u plus c. For a final step, we can resubstitute 3x for u, and also we can clean up the squares underneath the radical. So negative 1/2 times the natural logarithm of 2 plus the square root of 4 minus 9x squared over the absolute value of 3x plus c. Again, we're just learning new functions to do this with. The same differentiation and integration rules that we used all along still apply here. We just have the new hyperbolic functions and inverse hyperbolic functions to do them with.